fluid transport.
This meeting is being recorded.
Yeah, you can carry on.
Okay. So we'll be starting with rheology of non-Newtonian fluids. Now, when you talk about rheology, it's the science of the formation and then flow of material. So rheology is like you looking at how materials deform and then how they flow. But then this is specifically to fluids. So the science of the formation of flow of materials is what you term as rheology. This is for fluid transport. Now we are not concerned with the non-Newtonian fluids because we are not with that easy to understand. So in this course, we are not concerned with non-Newtonian fluids. Ability to called a fluid. Now we can have different types of fluid. There are two main types of fluids. Then non-Newtonian fluid and then the Newtonian. Now the non-Newtonian fluid elastic. I said we'll be looking at the non-Newtonian, so we wouldn't waste much time on the Newtonian. Please, can you hear me?
Yeah, Francis, we can hear you, but the line keeps breaking. Yeah, Francis. No, we can't hear you now.
You can't hear me.
Okay, we can hear you now.
Okay. Yeah, so under the non-Newtonian fluids, we have pure viscous, have time independent, and then time dependent. So we're going through all these types of fluids from the non-Newtonian fluids to the time dependent and the time independent. Now, with the Newtonian fluids, they obey Newton's law of viscosity, which states that shear stress is directly proportional to the shear rate. And to get rid of the proportional sign, we bring a constant here, and this constant is called apparent viscosity for non-Newtonian fluids. But then for Newtonian fluids, it's called viscosity or just dynamic viscosity. So Newtonian fluids, they are a type of fluids that obey Newton's law of viscosity, which is this. Please, is the line okay?
Yeah, it's fine. We can hear you now. We can hear you now.
So the Newtonian fluids obey Newton's law of viscosity, which is the shear stress applied to a fluid is directly proportional to the shear rate. And then when we want to get rid of the proportional sign, we bring an equal to sign and then add a constant here. So this constant is called viscosity for Newtonian fluids. But then for non-Newtonian fluids, we call them apparent viscosity. So in general, let's call it apparent viscosity. Now, when it comes to the non-Newtonian fluids, they do not obey Newton's law of viscosity, which is this formula. Right? So the apparent viscosity is not a property of the fluid in the same way as Newtonian viscosity. So when you talk about the Newtonian fluids, this viscosity is a property of the fluid. So let me take water like this. Water has a viscosity, and that viscosity is constant based on the properties surrounding with that temperature, with that particular water we are talking about. But then for the non-Newtonian fluids, the viscosity here is not a property of the fluid in the sense that it changes depending on the conditions like temperature, pressure, your shear stress, and your shear rate. Now let's compare Newtonian fluids and the non-Newtonian fluids. There is no such linear relationship between the shear stress and the shear rate. This is for the non-Newtonian fluids, as opposed to the Newtonian fluids, where we have this expression being held, right? So with the Newtonian fluids, realize that our shear stress here is proportional to our shear rate. But then for the non-Newtonian fluids, there is no linear relationship between the shear stress and the shear rate. And also, the apparent viscosity is not a property of the fluid. Yes. So most non-Newtonian fluids have apparent viscosities, which are relatively high compared with the viscosity of water. So with this one too, I think we can find much information on the next slide. So when you get there, you understand it better. Looking at the Rheology example, so this is a chart which has the different types of fluid based on the time, and then those which are time dependent and then time independent, and also the Newtonian and the non-Newtonian fluids. Now, when you look at this, realize that the Newtonian fluid it has a linear graph. So as the shear stress increases, the shear rate also increases. So they're directly proportional. But then when you talk about the non-Newtonian fluids, which are the Bingham plastic, pseudo-plastic, and the dilatants. So from here, realize that all these, the Bingham, pseudoplastic, all fall under a broad category known as the non-Newtonian fluids. And because the Newtonian fluids obey this, which is direct proportional to the shear rate, from the graph, realize that as the shear stress increases, our shear rate also increases. And that's the Newtonian fluid. So the rest, which are the non-Newtonian, realize that they do not have or they do not exhibit a linear response. When you look at the pseudoplastic, for instance, it increases slightly, it curves a little, then it increases again. When you look at the dilatant too, the same way. It's not linear. And then with the Bingham plastic too, when you look at it carefully, you realize that you have to increase the shear rate to a certain point before you can actually see the shear. So you have to increase the shear stress to a certain point before the shear rate start also increasing. So these are examples of Newtonian fluids: water, air, and I don't know if this is alcohol or something, but realize that with the Newtonian fluids, they are mostly they are not a mixture, right? Yes. So and their shear stress increases direct proportional to their shear rate. So when you look at water, for instance, the viscosity of water wouldn't change that much. Right? Looking at this water like this, regardless of the amount of shear stress you impose on the water, the viscosity will still be the same. Right? The same applies to the air and then this fluid also. So these are all called Newtonian fluids. Please, do we get it? Please, do we get it? Please, do we get it?
There's no response yet, but I think you can go on.
Okay. Okay. So with the examples of the non-Newtonian fluids, we have the PEP students. You realize that with the PEP students, you have to actually press or increase the shear rate to a certain point before the PEP student actually comes out from the container. And then this also, like a paint, you have to increase the shear stress before the paint can actually move, and this particular fluid too. So as compared to this, realize that the non-Newtonian fluids as a whole, looking at this graph, so we can see that the purpose is going to be something similar to this, because we need to actually increase the shear stress to a point before we can see the shear rate. And then the paint also. So these are all examples of non-Newtonian fluids. Now I want to look at the subdivisions of non-Newtonian fluids. The very first one we're looking at are the viscoelastic fluids. Now in the viscoelastic fluid, they exhibit an elastic response to changes in shear stress. So when you apply the shear stress to it, shear stress mean like you stirring or stretching something. So when you apply the shear stress to the fluid deforms. Maybe it can move to a certain point. But the moment you remove the shear stress, then the fluid comes back to its original position. That's what we term as viscoelastic fluids. So examples of viscoelastic fluids are flat dough, egg whites, polymer solutions like nylon and butane. The moment you apply the shear stress, they deform, or let's say they move. But then when you remove the shear stress or the force that you're applying to it, then it tends to go back to its original shape or its original form. So let's watch this video. So realize that as we are stirring, the fluid starts moving, right? So at this point, we are stirring, the fluid starts moving. Now, when we stop stirring, you see there is the fluid coming back to its original position. You can see that here. So these types of fluids are called viscoelastic fluid. Now we also have pure viscous fluids. Another pure viscous, please, we are looking at the types of fluid based on this chart. Right? So we started with the fluids, non-Newtonian fluids and then the Newtonian fluids. And then under the non-Newtonian fluids, you have the pure viscous and the viscoelastic. We've spoken about the viscoelastic. So now we are coming to the pure viscous. So under the pure viscous, we have time independent and then time dependent. Then there are also different types, another time dependent and a time independent. So you have to look at that too. So we are now in the viscoelastic fluids. The next thing to look at is pure viscous fluids. Now another pure viscous fluid from the chart, you realize that there are two divisions. You have the time dependent and then the time independent. But first of all, the difference between the pure viscous and then the viscoelastic is that the viscoelastic fluids, the fluids tend to come back to its original shape or its original form after the shear stress has been removed. But then the pure viscous is not like that. The pure viscous depends on time. So another pure viscous, some depend on time and then some do not depend on time. But then looking at pure viscous and viscoelastic, the viscoelastic comes back to its original shape after the shear stress has been removed. And then the pure viscous will come back to its original shape. So another pure viscous, we have time independent and then the time dependent. With the time independent fluids, there are those whose properties are independent of time or duration of the shear. So no matter how much or how long you are trying to impose the shear stress, the viscosity wouldn't be changing, right? The properties, or let's say the viscosity, that's what you're looking at. The viscosity depend on time. So the less viscous it becomes. So it's either it becomes more viscous as long as you apply the time. Sorry, as long as you apply the shear stress, or it becomes less dependent on time. So under the time-dependent fluids, we have the ones with viscosity decreases with time. So when it is fluid and the viscosity increases with time, we call it rheopectic fluids. So you just have to take note of this. With time. With time.
Francis, we can't really hear. Your line is breaking. Hello, Francis.
Can you all hear me?
Yeah, we can hear you now. Can you please go back to the previous one? I think they might have missed some things. Yeah,
Is it this one?
yeah, please go over it because your line was breaking when you were going through.
Okay. So I was saying that when you look at the chart here, under non-Newtonian fluids, there's a broad category, pure viscous and then viscoelastic. Now we've looked at the viscoelastic, so we are coming to the pure viscous. And I was saying that the main difference between the pure viscous and then the viscoelastic is that the viscoelastic, the fluids tend to go back to its original shape after the stress has been removed.
This meeting is being recorded.
But then with the pure, but then
Francis, please, we can't see your screen. And then there's a little feedback.
okay. Please, can you all hear now?
Yeah, we can hear you now.
So with the viscoelastic fluids, the fluids tend to move back to its original shape after the shear stress has been removed. And then with the pure viscous fluids, it's not like that. The fluid will not move back to its original position after the shear stress has been removed. So this is the main difference between the pure viscous and then the viscoelastic. And under the pure viscous fluids, there are subdivisions. We have the fluids which are time dependent and some are also time independent. With the time independent fluids, there are those fluids whose properties. So here we are looking at their viscosity. That is the main property in focus. So their viscosity are independent of time or the duration of shear. Right? And then with the time dependent, like the name goes, their viscosity or their properties depend on the duration of shear. Right? So if the viscosity depends on time, it's in either this time or it's time. It's with time or decreases with time. So when the viscosity when the viscosity decreases with time, then the fluid is called a digotropic fluid. But then when the viscosity increases with time, then it's called a eupectic fluid. Please, are we okay? Please, are we okay? Please, are we okay?
Yeah, someone said yes, we can
So
continue.
under the time-dependent fluids, we have the digotropic fluids, and these are the type of fluids in which their viscosity decreases with time. And then for the eupectic, their viscosity rather increases with time, or as long as you're applying the shear. So the more you're applying the shear, the more it becomes more viscous. So with the time-independent fluids, there are also different, categories of the time-independent, or let's see, types of time-independent fluids. You have the Bingham plastic. Again, we are looking at this chart here. Right? So another time-independent, we have the Bingham plastic, pseudoplastic, and the dilatant. So with the time-independent fluids, we have the Bingham plastic. And the Bingham plastic do not produce motion until some finite yield stress has been applied. So when we look at the chart from this graph, realize that with the Bingham plastic, before we can see the shear rates, the shear stress has to increase to a certain point before we can see the line coming. Right? So it means that the Bingham plastic they are fluids. Yes. So they are type of fluid that do not produce motion until some finite yield stress has been applied. And then this yield stress is the minimum stress you need for the fluid to move or to deform. Right? In this course, deformation is like saying the thing is moving. Right? So at stresses below the T naught, which is our yield stress, they behave like solids in the sense that they do not move. So when the stress you are applying to the fluid is lesser than the yield stress of that fluid, the fluid will behave like a solid and wouldn't move. When the stress goes above the yield stress, then we can see the fluid moving. And then the plot of your yield stress versus your shear stress versus your shear rate becomes linear. So we can look at it from this diagram. Yes. So after we exceed our yield stress, realize that our shear stress versus our shear rate become a linear. Yes. So this is the formula which is applicable to the Bingham plastic. Realize that this is not equal to that of the Newton's law of viscosity, which is just your shear stress being proportional to your shear rate, right? So with this one, when our shear stress becomes more than our T naught, then the fluid starts moving. If not, the fluid wouldn't move. So examples of Bingham plastic fluids are sewage sludge. I think the most commonest one we can relate is the toothpaste and then the tomato ketchup. So the toothpaste, when it's there, it's something solid. It doesn't move, but then you have to press it. Apply some stress before it starts moving. The same applies to the tomato ketchup. Now, still under the time-independent fluids, you have the pseudoplastics and then the dilatant. With the pseudoplastic, it's like we actually merge these two because they are opposites, something like that. So the pseudoplastic and then the dilatant, they all obey the same law, which is called the power law. But then the power law is tau equal to k multiplying this to the power n. So based on the n, then you can differentiate between pseudoplastic and then the dilated fluid. And then our n here is our fluid behavior index. So when n is equal to 1, realize that when n is equal to 1, we get a Newtonian fluid, right? When n is 1, it becomes the Newton's law of viscosity, and that becomes a linear function too. But then when n is less than 1, that's where you have acidoplastic. So when n is less than 1, that means this becomes a denominator, and then it's going to divide. It's no more a linear function. And then when n becomes greater than 1, 2, you have a dilatant. So in that case, it will still be positive multiplying, but then the power here wouldn't be a linear one, wouldn't be 1 to make it a linear. Right? So maybe if n is 3, that means our function here is not a linear function. So it doesn't obey Newton's law. That's why they are all non-Newtonian fluid. So pseudoplastics are the most common type of non. I think as we move, we get and the pseudoplastic is achieved, or fluid is said to be pseudoplastic when our n value here is less than 1. So when it's less than 1, then we have a pseudoplastic fluid. Right? So when you substitute it, here, we are seeing our n is less than 1. Right? So something like this. Our apparent viscosity here, when you look at the Newton's law of viscosity, we said that our tau here is equal to, and this is our apparent viscosity times our shear rate. So with the pseudoplastic, because they obey, okay, yes. So as our apparent viscosity here for the pseudoplastics is given by this relation, and you can have the proof on the next slide. Yeah. So from the power law, so if you want to, write the expression to fit the Newton's law of viscosity, which is the general case, which is tau to write this in this format, right? So you have to get something multiplying the Vx dy, but then this the Vx so factorize the Vx dy out. So when you factorize out, you are going to get when you factorize the Vx when it's first equation, right? So you are factorizing the Vx dy, so it becomes a denominator here, right? So when you multiply these two, this cancels this, and then we are getting this back. So when this multiplies this, like this cancels out, and then we are getting this back. So we haven't done anything to the equation. We just factorize the Vx over dy. So comparing it with the general case, this, we have our tau being equal to our tau here. We have the Vx dy being equal to the Vx dy here. So our apparent viscosity here becomes the whole of this. And that's how come we had apparent viscosity being equal to this. So still on the time independent. So we get apparent viscosity being equal to this. And what does this imply? It implies that the exponent here will be negative because we said that with the pseudoplastic, our n supposed to be less than 1. So if our n is less than 1, and then we have our apparent viscosity being equal to k multiplying this expression, our share with exponent n minus 1, and our n is less than 1, that means we are going to get negative. So what does this negative imply? Now, when it becomes a negative, then this expression here, this term here, will be a denominator. That means it's going to divide. So the moment it's going to divide, then it means that our apparent viscosity here will have an inverse relation with our share rate here. So can realize that as we increase, so if we increase our share rate here, then it means that our apparent viscosity is going to decrease. It's like an inverse relation. Please, you get it? So the more we increase our share rate, then our viscosity is going to decrease. The apparent viscosity decreases with increasing shear rate. That's for the pseudoplastic. These fluids are said to exhibit shear thinning. So anytime you have your fluid in which anytime you have a fluid in which the viscosity decreases with increasing shear rate, then that fluid is said to be exhibiting shear thinning. So examples of such pseudoplastic fluids are rubber latex, adhesives, polymer solutions, paper pulps. I think let's find the one that is very common to relate to.
Oh, even paint too.
Okay, it's paint there.
I don't think we added the example, but then it acts like a pseudoplastic sometimes.
Okay.
Yeah, so
Please, can you guys relate?
as you stir or as you mix it, realize that it becomes lighter and lighter.
Okay. Okay. Please, do you get it? So the more you are stirring the paint, the more you realize that it becomes very lighter. Yes. Or let's see, less viscous. Because we know viscosity, what viscosity means. So if we say we are decreasing viscosity, it means that the fluid is becoming more lighter and it can flow easily. When we say we are increasing viscosity, that means it's becoming more thicker and then it can't flow. So the more you stir your paint, you realize that it becomes less viscous or it becomes very light that it can flow. And still another time independent, you have the dilatants. So I said that pseudoplastic and the dilatants are like two opposites. Right? So whilst the pseudoplastic has the n less than 1, the dilatants have their n being greater than 1. And then they all follow the power law. And so as such, the apparent viscosity will still have the same formula. But in this case, our n here is greater than 1. Right? So this will be positive. When it becomes positive, it means that you are going to have a proportional relationship between your shear rate and then your shear stress. So the more we increase our shear rate, the more our viscosity also increases. Yes. So apparent viscosity increases with increasing shear rate. So as we are increasing the shear rate, our viscosity also increasing. And this is called shear thickening. Please, are we okay? So for such fluids, the more you are stirring, the more viscous it becomes. You can look for an example here, sugar solution. I don't know if you guys have tried something like that before. Please, who has tried something like that before? A sugar solution. No one.
I don't think so.
Okay. Yes, so we have a video here. So ketchup acts like pseudoplastic fluids. And then the dispersion of corn flour. So from this video, you can realize that the more the person stirs the solution here, the more thicker it becomes. See, the more you stir, the more thicker it becomes. I don't know if anyone can give us a practical example that we can all relate to. Thicker it becomes, and then yeah, so I think the sugar solution, I've tried it before. Then you can put your you can put your sugar on fire, and then you start to stir. You realize that the more you stir, the more thicker it becomes. And then if you can't relate to any, this video is there to help you. We will send you the slides so you can watch them carefully. So the more you stir the solution, the more thicker it becomes. Okay. So now we are moving on to the time dependent. And then when the time dependent, I mentioned two of them. I said the dixotropic fluids and then the eupectic fluids. So with the time dependent fluids, they possess a structure, the breakdown of which is a function of time as well as shear rate. So I was trying to say that the time here is the duration of the shear rate. Sorry, the duration of the shear stress. And then we classify them into two. It's either the viscosity increases with time or decreases with time. And then we said that when it decreases with time, it's called isotropic. And then when it increases with time, it's called eupectic. So with the dixitropic fluids, so they are type of fluid in which their viscosity decreases with time. So decreases with time means that we are saying that when we stop, or I mean, when the shear stress is being removed, the viscosity tends to decrease as time moves on. So examples of such fluids are the mayonnaise and then many paint as well. So you realize that with the mayonnaise, when you press, I don't know if there's a, okay, when you press it from the bottle, it starts flowing, right? But the moment you stop, pressing it or applying the shear stress, then as time goes on, it tends to the viscosity tends to decrease and then it goes back to its original position. Right? So that's the dictiotropic fluid. So with that one, when you stop applying the shear stress, the fluid starts becoming viscous again. And with the eupectic fluids, their viscosity increases. With the eupectic fluids, their viscosity increases with time. So we can actually keep the shear stress constant, right? We can keep the shear stress constant and then we'll be looking at just the time. So if let's say we are stirring something, and this also applies to the topic, it doesn't necessarily have to remove the shear stress. The shear stress is still there, but let's say as you apply the constant shear stress for a very long period of time, the viscosity tends to decrease, and that's the topic. And then for the eupectic, the shear stress is still constant. But then as it becomes constant for a very long period of time, they realize that your fluid viscosity tend to increase, right? So that's the difference. Did you get it now? I think there's a video here. Now, so this is the dictiotropic fluid. Now, please let's observe it very well. We are applying a constant shear stress. So the more you are applying a constant, this is dictiotropic, but for the eupectic, so something like this. There's a constant stirring. So here, when you say viscosity decrease, that means it becomes more lighter. So even though our stress here is constant, our and then we are applying it, the viscosity tends to increase in that case. So you see, after a while, it becomes easy, which implies that the viscosity has decreased now. We will send the slides to you, so you can actually take time and watch all the videos and get a clear understanding of it. Now with the eupectic, so the cell viscosity tends to increase. Right? So that's the difference. It doesn't mean we should actually.
Hello, Francis.
Hello, doc.
So I want to say one thing about all these non-Newtonian fluids. Do you see that none of them is a natural fluid? It looks like
Okay.
all of them are things that has been fluidized, like solid, which you have added some. So it's a combination of things, like a natural fluid has been added to some solid, and the solid is at the right concentration, such that it can still have some fluidized properties. Am I right?
Yes.
So it's never a pure stuff. Like it's never your water. It's never your any clear liquid. It's always like ketchup. Right? Ketchup is like tomato, but they've added some small flour to it to kind of make it, to thicken it up a bit. So it's always something that was not naturally fluid that has been made fluid. Am I right in saying that? A mixture of stuff. So if crude oil is one of
Yes.
them, crude oil has solids in there, liquids in there. Am I right in saying that?
Yes, doc.
So they are never like the fluid that you meet every day. It's always some form of intense agitation that has converted something to a fluid.
Okay. Thank you, doc. Yes, so the eupectic here. So the eupectic video here, realize that the more we apply that constant stirring rate, the fluid becomes more thicker and thicker. Yes, making the viscosity increase. Okay. So let's look at rheology in general, or so when you look at rheology in general,
Okay. Okay, so I would take this part. We'll just do a few more things and then we'll be done with this part. But then someone was asking about the diagram before the slide. Okay, and someone is also asking the difference between share rate and time. Because anything with rate means it is with respect to time. Okay, so I'll address these questions and then we'll continue. So the diagram before. Okay, so what we are just saying is that we have some amounts of shear stress, right? That is acting on the fluid. When we increase the shear stress, or yeah, when we increase the shear stress, we'll also have a corresponding increase in the shear rate. So it's just like the rheogram we've looked at so far. So I'm increasing the shear stress. It's going to cause an increase in the shear rate. And yesterday we spoke about the shear rate, which is equal to the negative of the velocity gradient, right? So as I increase the shear stress, it's going to be a corresponding increase in the shear rate. But what we are saying is that after a while, it is able to also come back, right? So just like what he said, if I have a particular fluid, like the one I have over here, and then I'm stirring it, I am actually there's some amount of stress I am inducing on the fluid. So it's also going to increase the shear rate, and that's going to affect its viscosity. The viscosity is going to change. But then after a while, it is also able to come back to what it was originally. That's what the diagram is just trying to say. So for thixotropic fluids, as we are increasing it, the shear stress, we'll have the shear rate increasing this way. It's not linear because it is not Hamiltonian fluid. And you remember when we were looking at the rheograms. So let me get there. Okay, good. When we're looking at the rheograms, right? Something like this for pseudoplastics, it was going upward. I think that's convex. Yes, right. When it moves this way, then it's the kind of fluid that would have its viscosity decreasing when we increase the shear stress there. When it's concave this way, then we have the viscosity rather increasing when we increase the shear. So if we look at the thixotropic, right, it's having that same um kind of initial curve upward here, like the pseudoplastic. So as I increase the shear, it's going to increase the sorry, the screen is as I increase the shear, it's going to increase, so it's going to reduce the viscosity, right? And then to be able to come back to the original thing. The same thing with the rheopectic. So as I increase the shear, it's going to increase the viscosity and then it will also come back. And then the next question about the difference between, okay, I think I didn't send this one. The next question about the difference between shear rate and time. So when we talk about shear rate, right, we're looking at um, how the velocity is going to be changing, um, how the velocity is going to be changing with respect to a given distance. So that's the velocity gradient, right? That's the shear rate. But then the reason why it is having the term rate in there, because you know that velocity is something that is with respect to time, right? So that is one thing. We are looking at it in terms of velocity. But then when we look at the time in this, what we mean by time over here, what we are trying to say is how long the shear force is being applied to our fluid, right? So I can apply a certain amount of force to the fluid. It will give it some kind of shear. There will be a certain velocity profile, right? There's velocity in there. But then how long am I going to apply that force? I hope it makes sense. So if you want to make this a little bit more practical, let's say I have a block, right? And then I use some amount of force to hit the block. It's going to move with a particular velocity, right? So that velocity there is something that is with respect to time, is the change in distance over the change in time. But then if I apply the force on the block for long, how far can I take the block? If I apply the force on the block for just a short amount of time, how far can I take it? So in all things, the velocity might be the same, but then how long am I applying the force to it? Is that okay? So that's what we're looking at, the difference in the shear rate and the time. I'm not saying that yes, anything rate means it is with respect to time, but then what we are saying here is that there's a force that is acting on the fluid. And that force is going to introduce some kind of velocity gradient. That's where the shear rate comes in, because velocity is something with respect to time, right? That's why it's a rate, right? But then the time that we are looking at when we look at isotropic and rheoperic fluids is how long that shear force is being applied to the material we are considering. Okay. Then all the things we've spoken about, we can look at rheology in general. So we say rheology is just looking at the flow of fluids and the different kinds of behavior fluids have, right? So when we look at a good toothpaste, for example, it has to be a Bingham fluid so that it wouldn't easily be squeezed out of the tube, right? So something like toothpaste, what we are just trying to say is that we said for Bingham fluids, there has to be a minimum stress that we exert on it before it will begin to flow. Imagine if your toothpaste was like water and it's in the tube, it would easily come out, right? When you just open it, you don't want such a thing. So it has to be the kind of fluid that will require that you apply some initial amount of force up to a certain limit before it will now begin to flow, right? When we look at paint, for example, we are saying that paint should be a thixotropic Bingham fluid. So the same thing, it should be a Bingham fluid because you want to apply some amount of force on it before it begins to flow. And it should be thixotropic so that when I'm stirring it, it will become lighter, right? So when the paint is in the can, it's very viscous so that the pigment will not settle to the bottom. So realize that paint is a mixture of things, just like what Doc was saying. It's a mixture of different things that gives us this kind of fluid. So paint is a mixture of things, right? And one of the things in the paint is a pigment, that the thing that gives it the color. If the paint was not viscous enough, the colorant will settle to the bottom, or the pigment will settle to the bottom, but we don't want that. That's why it has to be very viscous. And that's where the Bingham fluid part comes in. So it's going to have that high viscosity until we introduce some amount of force to it, right? And then when we stir it, it becomes less viscous. That's where the thixotropic nature comes in. And now we can brush it onto the surface of whatever material we are working with, right? Then when we are brushing it onto the surface, we are going to have the viscosity reduced so that the paint can now flow sideways. So this is still with respect to it being thixotropic, right? Then when we leave it, the viscosity should increase again so that it will not run down the wall. So if you look at the diagram that someone asked me to explain again, paint is thixotropic. When I stir, it becomes lighter and I apply it to the wall. When I stop, when I'm done applying it to the wall, it should start to thicken again. If it doesn't thicken, it would now begin to run down the wall. That's not what we want, right? So for thixotropic, when we introduce the shear, we are reducing the viscosity. And as we are taking the shear out, it's going to come back to the original viscosity, right? But then it is still something that is done with respect to time. Now, let's even consider this again. We are saying that it's with respect to time. If I'm stirring the paint, right, and I stir for like maybe just 20 seconds, it will become lighter. But then it wouldn't be as light as if I should stir it for about 2 minutes, even if I'm using the same amount of force to do the stirring. That's why we are saying it is with respect to time. Time is also very important with these things. Is that okay? So over here, we have a table that has some materials with their corresponding viscosities. Right? So these are just examples of some non-Newtonian fluids and then their viscosities. Right? So, and Francis took us through rheology, that's the behavior of fluids. I'll just take us through the introductory parts of fluid flow, and then we'll continue with that from tomorrow. Okay. So when a fluid is flowing through a tube or over a surface, then we are saying that the pattern of the flow is going to vary with the velocity, and then with the physical properties of the fluid, and then the geometry of the surface, right? So there's a certain pattern that fluids have when they are flowing. And these patterns are going to be dependent on the velocity the fluid is coming with, the physical properties of the fluid. So something like its velocity, its density, all these things, right? And then the geometry of the surface. So if we have a flat surface, if we have a rough surface, if it's moving through a cylindrical pipe, if it's moving through a square kind of tube, something like that, right? So the way the fluid would look like, or the pattern that the fluid flow would have, would be dependent on some of these properties. This was first examined by Reynolds. So we'll get to a point where we now speak about Reynolds number, and we'll understand that a bit more. I think that will come in with tomorrow's discussion, right? So you can just take note of the name. This is one of the most important names you come across in fluid transport. So when we look at fluid flow through a pipe, we can consider it in two ways. We have what we call laminar flow, and then we have what we call turbulent flow, right? And then there's a point where we can have a transition from laminar to turbulent flow. Okay. So when we talk about laminar flow, what we are saying is that the layers of the fluid are going to move over each other smoothly. So there's no mixing perpendicular to the axis of the pipe, and the Newton's law of viscosity holds. So it is also called viscous or streamlined flow. Okay, there's a question. Can we say air affects viscosity of some substances because of their chemical composition due to their reactions with the air when they come into contact with the air? Okay, when we are looking at the viscosity, right? Let me put it this way. We can have some reactions that would happen that can change the viscosity of something, but then that is a reaction happening to give us new substances. Is that okay? But when we talk about viscosity, or when we look at the analysis we are doing here for fluid transport, our interest is in this formula. So I think this will take us back a bit. Our interest is in this formula. So what we want to look at is this viscosity here, right? The effects or how the viscosity is going to be affected by things like shear stress. That's this term over here, and then the shear rate. We're not looking at any reactive system. If we have a reaction happening, then we are going to get a new material. That's why the viscosity can change. So yes, it's possible that you can have a reaction happening that will change the viscosity of something. All right, now we are looking at it from the point of momentum, from force. Is that okay? So we are looking at the effects of forces and of momentum and viscosity. That's why when we were speaking about this yesterday, we spoke about the fact that we are considering momentum transfer. Is that okay? There's mass transfer, there's heat transfer. We are considering momentum transfer, right? So sorry for the background noise. So what I was saying was that for laminar flow, for the definition here, what it's saying is that the layers are going to move each other smoothly. So there is no mixing perpendicular to the axis of the pipe. And Newton's law of viscosity holds. So another name for laminar flow is viscous flow or streamlined flow. Now let's look at the animation on the animation on the right. At every point in time, the fluid is moving, right? So even the points where it looks like it's stationary, it's actually moving. So I'll wait for it to get back to that point and I'll show you something. When we talk about mixing perpendicular to the axis of the pipe, this is the axis of the pipe, right? So you realize that even at the point where it looks stationary, the fluid is actually moving, right? In that case, this is what we call laminar flow. So in this form, it is moving. Then when it starts becoming turbulent flow, we can see that it is mixing perpendicular to the axis of the pipe. So that's the axis of the pipe. Perpendicular to it is this way. So we can tell the fluid is now mixing along that line. Is that okay? So for laminar flow, usually happens with things like very low viscosity. There's not going to be any mixing, right? The fluid sometimes even look like it's not moving at all, but it's actually flowing. And so this, what we see right now is laminar flow. Then it now starts to become what we call turbulent flow. So for turbulent flow, if you look at the definition, it's saying that at higher velocities, the flow becomes turbulent. It's characterized by rapid chaotic motion in all directions in the pipe superimposed over the axial motion. So what we are just trying to say is that there's now some chaotic motion, there's some random motion that is happening in all directions over the axis of the pipe, right? And then there's mixing by eddy motion. So we'll speak about eddy motion very soon. There's mixing by eddy motion between the layers. And then even in the overall steady flow, the velocity at a point can fluctuate. Right. So what we are just trying to say about that is it's possible that we might even have steady flow happening or steady states steady flow happening, but then there's going to be some fluctuation in velocity around a certain mean value. So it's steady because we're just considering a mean and average. Remember for steady, we said that it's not supposed to change at a point. But for turbulence, we can have a case where we can consider it to be steady, but then we are just saying that the velocity at a point, it can be changing, but we're just going to assume that it's an average velocity. That is not going to change. Is that okay? So that's it for laminar and turbulence flow. Now, if you look up here, you can see a certain number, R is equal to 547. That's what we call the Reynolds number. And I said we talk about that later on. I remember I mentioned that Reynolds is if there's a question, I'll answer it. So remember, we spoke about the fact that Reynolds number is something important to look at. Realize that if you look at the animation rate, when Reynolds number is quite low, we have laminar flow. As it starts to increase, so you realize that the number increases here and then it starts to become turbulent. So just take note of that. It will become very important to you in subsequent discussions, right? So someone is also asking that is laminar flow uniform? Remember we said for uniform flow, it means that the properties at a point are not going to change with respect to time, right? And on a large scale, yes, laminar flow is uniform, but then there can be a point where it's not uniform for reasons such as it might be laminar, but then maybe as the inlet, it's at one temperature. Later on down the pipe, it's at another temperature. So now it can be steady, but then not uniform. I'm going to talk about the difference yesterday. So we can have laminar flow. That can be steady state flow. But then the flow throughout the entire pipe may not necessarily be uniform. Is that okay? And we can also have laminar flow that is uniform. Please, is that okay? So we spoke about the difference between uniform, non-uniform, steady, and then unsteady yesterday. So I hope that makes sense to us. And please, the one who asked the question, I hope you are fine with the answer. Okay, then that's good. Now I said we'll speak about eddy flow as well, right? So we said that for turbulent flow over here, said that for turbulent flow, there is a mixing by eddy motion. So now let's talk about eddy motion, right? We say when we speak about eddy motion, we're talking about turbulence flow. So eddies are what we call small pockets of fluid particles that are moving in all directions. And they are moving at all angles to the normal line of flow. So what are we just trying to say? If we look at this, let's say this is a pipe, right? The fluid, we have a pocket of fluid. So this one here can represent a pocket of fluid particles. They are moving in this particular direction. The pockets of fluid is moving in this particular direction. Right. So they are moving in all kinds of directions and then in all angles, different directions, different angles, but then they are clusters or collections of pockets of fluid particles. Now, turbulent flow consists of a mass of eddies of various sizes coexisting in the flow stream. So when we have turbulent flow, we can have different sizes of eddies. Right? So we can have maybe one pocket of fluid here, which is larger than another. Right? The thing about eddies is that usually large eddies are formed and then they break down into smaller eddies, which will further break down into even smaller ones, right? Also, the point where smallest eddies will disappear. Is that okay? So if we look at the animation down here, right, I think I'll wait for it to start again and then we'll see what I'm talking about. If you look at the animation, realize that there's a certain fluid flowing, right? And then there are two blocks. The black parts are two blocks here. When it starts, we see this part here, this huge circular thing that comes down here. That's an eddy, right? And it now starts to break up and become smaller and smaller. As it breaks up, it's forming smaller eddies until all of them disappear, right? The size of the largest eddy is comparable with the smallest dimension of the turbulent stream. So what we are trying to say is that the largest eddy you can form, right, has a relation to the smallest dimension of your stream you have. So maybe if it's flowing through a pipe, right, the smallest dimension of your pipe might be the diameter of the pipe. So there's a relation between the largest size of eddy you can get and then the size of the pipe that you are having. I just trying to say that there's a certain relation between them. So you can be able to determine how large your eddy is going to be or how, the diameter of your eddy based on the smallest dimension that your stream has, right? And then there are just a few facts for you to just take note of. The diameter of the smallest eddy is about 1 millimeter. It contains about 1,060 molecules. So all eddies are of macroscopic size. The turbulence flow is not a molecular phenomenon. So eddies don't happen on the microscopic level, they are macroscopic. That's why we say that they are um, pockets of fluid. They are collections of fluid particles. They are not individual fluid atoms, right? So it's a macroscopic phenomenon, not a microscopic or molecular phenomenon. So that's one thing to take note of, right? When we look at the flow within an eddy, this is important to note, it is laminar. So even though eddies contribute to what we call turbulent flow, if we pick just the eddy itself, just one eddy, the flow in the eddy is going to be laminar. Is that okay? So please, are there any questions before we continue? Okay, sure. Please, are there any questions before I continue from there? Okay, then let's move on then. So we said that any eddy will possess a definite amount of mechanical energy, right? It has mechanical energy because there's some kind of motion and everything associated with it, right? But then the energy of the largest eddies are supplied by the kinetic energy of the bulk flow of the fluid. So the eddies get their energy from the kinetic energy that the entire fluid is moving with. And then this energy is transferred as energy of rotation along a continuous use of smaller eddies. So if we look at the animation once again, as the fluid flows, right, the eddy forms, and we see that it is actually rotating. It's getting that energy from the bulk of the fluid. That's what we are just trying to see. It's getting its energy from the bulk of the fluid. And then that energy is going to cause it to rotate. So there's some kind of rotational energy that it transfers and it is transferred into, right? But then the mechanical energy, we don't really see it being converted into heat when the eddies are breaking up. So the thing is that when the eddies are breaking up, they are losing energy, and we expect to see the energy in some other form. Remember, we said that energy cannot be created or destroyed. It can change from one form to another. So if it's breaking up, where is the energy going to, right? Ideally, when the mechanical energy is being lost, we expect it to be translated into some form of heat, right? But then we don't see, remember, I didn't say it doesn't happen. I said it is not appreciable. So the amount of heat energy generated is quite small, right? So most of that energy is still stored within the smaller eddy. That's what it implies. So if we have an eddy with mechanical energy and it's breaking up and we're not seeing so much heat being involved, it means that most of that energy is still stored within the smaller eddies that it is breaking up into, right? And that energy is not going to be available for maintaining pressure or for overcoming resistance to flow. So we usually don't really consider the energy of the smaller eddies, the mechanical energy of the smaller eddies, because it doesn't have any significant contribution to um, keeping the pressure of the system or resisting the flow in the system, right? That's what we're just trying to say by this point over here. Right? So I'll just take it again. When we have large eddies, there's some mechanical energy that comes in that causes some form of rotation, and it comes from the bulk of the fluid. But what happens is that the eddies now start to break up, and when they break up, we expect them to lose energy, but we don't see a significant change in the energy, right? So it means that the energy is still stored within the smaller eddies. But then that energy that is stored, it is not um, so significant when it comes to maintaining the pressure in the system or maintaining or causing some kind of resistance to flow in the system, right? And then as chemical and petrochemical engineers, we are interested in the pressure of our fluid moving through maybe a pipe, the resistance that the fluid is encountering moving through a pipe. If these eddies are not going to contribute significantly to that, then we are not really concerned about their energy, what is being stored within them, right? And then when the smaller eddies now begin to dissipate or when they disappear, then the mechanical energy that was left in them can now be translated into heat. And that one is what is important to us. Is that okay? So we have large eddies. As they are breaking up into smaller eddies, we don't see a significant change in the energy in the system, right? But then when the smaller eddies now disappear, then we can now have their energy being translated into heat. Is that okay? We can now have their energy being translated into heat. Please, are we fine with this up to this point? Please, are we okay up to this point? Okay, that's very good then. So we can also consider, okay, that's very good. So we are seeing here that turbulence may be generated from contact of the flow stream with solid boundaries. We call that raw turbulence. Or contact between two layers of fluid moving at different velocities. We call that free turbulence, right? So what we see over here in the animation, for example, is raw turbulence. We can see that there are solid boundaries and it's causing some kind of turbulence flow in the fluid. Is that okay? So we see as the animation is happening, there's a fluid moving over some solid blocks. And as you can see some kind of turbulence being formed, right? Realize that, I think, let me try and draw on it. Realize that up to this point here, everything looks almost the same. It doesn't really look like there's much happening here. But then as soon as it crosses the block, you can see that there's now some kind of turbulence being formed here. Do we see that? So realize that it's starting out laminar, right? But then as it crosses the block, then you can now see the turbulence now starting to happen. This is what we call raw turbulence. So the turbulence is coming about as a result of the turbulence is coming about as a result of there being a certain contact of the fluid with the solid wall. And we can also have what we call free turbulence, right? So free turbulence is like something um like a plane moving through air, right? When it starts to move very fast through the air, we realize that there's some form of turbulence that's going to be generated in the air. I think there was an image, but we don't have that here. It's in the original material which we sent to your page. So you can see that image there. I think I should have added it so that it will be easier to visualize. But for free turbulence, you just have two fluid layers moving at different velocities, right? So what I'm trying to say is that, okay, let me try and get the image. I think I should have it opened. Okay, I do, but let me open it from here. Minutes. So this is the image I'm talking about. Yes. So realize that as the plane is moving through the air, right, what's going to happen is that because of how fast it's moving, the layer of air just around it is going to have a different velocity from the layer of air further away from it, right? So the interaction between the layer of air just coming from where the plane left and the layer of air around it is going to cause this kind of turbulence happening. Is that okay? Right. So for wall turbulence, it comes about as a result of contacts with the fluid with a solid surface. Right. But then for free turbulence, it's as a result of a contact between two fluid layers moving at different velocities. So the fluid layers are moving at different velocities, and then they will constitute what we call free turbulence. Right. Okay. So I'll go back to the slides. Okay. Um, Yes. So wall turbulence appears when the fluid flows through closed or open channels or past solid shapes. So we've already spoken about that, immersed in the stream. In turbulence flowing pipes, the largest eddies have a length of 25% of the pipe diameter. So remember we said the size of the eddies, right, are comparable with the smallest dimension of the flow or the system we are dealing with. So we can see a relation here. So for turbulence flowing pipes, right, the largest eddy you can get would have a length that is about 25% of the diameter of the pipe. Right, so there's a certain relation you can have between the size of the eddy and then the smallest dimension of the pipe. Right. Then when we look at things like ships and airplanes, right, the largest eddies we can get would be a fraction of the size of the ship or of the airplane. Is that okay? So free turbulence appears in the flow of a jet into a mass of stagnant fluid, or when a boundary layer separates from a solid wall and flows through the bulk of the fluid. Right. So we'll speak about the boundary layer things tomorrow, God willing, right? Okay. Now we can have what we call the transition region. So remember we mentioned that we can have a transition from laminar to turbulent. So laminar flow can exist in conditions in which it is not a stable form. What we mean by that is we can have a condition where it is laminar, and then it is starting to change to turbulent. So we can have it switching slightly to turbulent, coming back to laminar, that kind of thing, right? But I think that it fails to switch to turbulence flow unless some outside disturbance, such as microscopic roughness of the pipe or very small vibrations in the equipment, trigger the transition. So let me use this animation to explain it. Remember that we said at this point the fluid is actually flowing, right? The fluid is actually flowing, but it looks stationary. Then we now see that it now starts to sort of have some kind of perpendicular motion, or we now start to see some kind of change happening. What we are just trying to say is that for laminar flow, we can get to the point where it just stops becoming laminar. So I think if you look at it this way, right, this is still laminar. And then we see that part where it's just had that kind of wave-like motion. That's the kind of thing we're talking about. So usually it will still stay laminar. It wouldn't yet turn to turbulent until we introduce some kind of disturbance. So maybe there's some kind of vibration that happens in the pipe that will cause it to now start changing to turbulent flow. Or maybe the pipe is a bit rough. So the roughness in the pipe will now start to cause it to begin to change to turbulent flow. And remember we said Reynolds number can be used to determine whether we have laminar turbulent flow. If you look at it critically, realize that when we move from 355 to 374, so this is 374, right? Then we now started seeing it start to become, we now started seeing that slight motion, but then it was still quite laminar for a while before we increase it again. That slight motion, that was a little disturbance that we saw. So we can see it's still 374, but we still see those little changes. It's because it is mostly laminar, but then there are some disturbances that are causing it to now start switching to turbulence. I hope that makes sense to us. Right, so we can have it to be largely laminar flow, but then it is not so stable. If we should add a disturbance, it will now start beginning to change to turbulence flow. Is that okay? Okay, so what I'm saying is that in the transition region, the flow can be laminar or turbulent, right? And then the pressure drop of the fluid can suddenly change. So under some circumstances, the flow can alternate back and forth, being laminar and turbulent. So we can have the pressure drop oscillating between higher and lower values. Or when we have a constant pressure drop, then the velocity would be moving between higher and lower values. So realize from the animation that when we are having laminar and turbulent flow, we saw that there was a change in the velocity, right? We realized that the fluid started moving a bit faster. So let me show that again. Realize that when we have this moving from laminar to turbulent, right? realize that the fluid is actually looking as though it's moving faster. So wait for it to get to the very turbulent region. Right. Okay. So that's what we're trying to say from that. Okay. And we are saying that it can alternate between laminar turbulence, that kind of thing. So when we come back to this animation we had over here, remember we said that this first part here is laminar, right? We see it's mostly laminar. We don't see so much change happening. So this side is laminar, but then this side is turbulence. So where the transition region going to be is going to be this portion over here. If you look at it, you realize that there are some points where it almost looks as though it is stationary. Don't see that there are some points where it looks like there's some fluctuation happening. Right? So we have laminar transition and then turbulence. And then this transition region, you can have this switching between laminar and turbulence flow. Is that okay? Okay. So for almost all flows of gases and liquids in ordinary sized pipes are turbulent. So when we have liquids and gases flowing through pipes, most of the time, what we have is turbulence flow. The only exceptions we have are for fluids that are more viscous than water. So when we have very viscous and thick fluids and they are flowing, we really don't see a lot of turbulent action in there, right? So imagine you have something like um cement flowing. I think cement is not good. Let's say you have something like ketchup or honey flowing through a pipe, right? It'll be very difficult for you to see turbulent action happening. So usually for very viscous fluids, we really don't see a lot of turbulent action happening, right? But then when we have very small tubes or other flow passes, then the flow is normally going to be low. So yes, we can have tubes that are very, very small. When we have very small tubes, then usually we have laminar flow, right? So the flow in the hearts and the major arteries near the heart in our bodies are usually turbulent. And I think that makes a lot of sense because the heart is going to pump the blood with a lot of force. It's going to move with so much force and velocity. So you see it having some kind of turbulent flow. Remember we said that turbulent flow happens with very high velocities, right? And then the rest of the blood flow in our body is laminar, as is the flow in filters, in underground water, and then in oil fluids, right? Okay. Then river flows are mostly turbulent, and then the main flows of the atmosphere are turbulent. So I think turbulence flow is actually more common um, than laminar flow. But the laminar flow is, I mean, it's not something that we don't see. It happens often as well. Is that okay? So these are just examples of situations where we can have laminar and turbulence flow. So we'll be ending with ideal flow for today. And then from tomorrow, we'll continue with boundary layer flow. And then we'll take it from there. Okay. So for ideal flow, it is also called potential flow. When we talk about an ideal fluid, it is an incompressible fluid which has zero viscosity. So now let's look at this critically. We spoke about what incompressible fluids are. We said that their densities do not change significantly when we have changing conditions, right? Like temperature and pressure. Those are incompressible fluids. Now, if we assume the fluid also has a viscosity of zero, it doesn't have any viscosity, then we can call that an ideal fluid, right? It's not a real fluid. It's an ideal fluid. Is that okay? So there are two important characteristics for potential flow or for ideal flow. So there are no circulations or eddies that can form within the stream. So we can also call it irrotational flow. Is that okay? The formation of eddies and all those things has a lot to do with the viscosity as well. So if viscosity is zero, eddies won't be formed. And if eddies are not formed, then we don't have that kind of rotational flow that was coming from the eddies. So we can also call ideal flow or potential flow irrotational flow. It means there's not going to be any rotation with the molecules of our fluid, right? And then we are saying that friction can also not develop. So there's no dissipation of mechanical energy to heat. And I think that makes a lot of sense. But remember, we spoke about the fact that a minute. Okay, sorry about that. And I think there's a question. Okay, I'll address the question when I'm done with this part. So friction can't develop, right? The reason why friction can't develop is because remember, friction in the fluids has a lot to do with viscosity. We spoke about it yesterday, but viscosity has to do with the internal frictional forces in the fluid. If there's no viscosity, we won't have friction being developed. Right? And if there's no friction, then we won't have mechanical energy being translated into heat. right? So we spoke about this yesterday as well. If we are walking on the ground, the soles of our feet are having some kind of friction with the ground, right? And then there's some form of heat that can be generated. So we can have friction can cause mechanical energy to be translated into heat because there is no viscosity, or we are assuming that our fluid has a viscosity of zero, then it means that there can be no dissipation of mechanical energy into heat. Now, potential flow can exist at distances not far from the solid boundary. So there was a guy called Pranzo, and he stated that except for fluids moving at low velocities or possessing high viscosities, the effect of the solid boundary on the flow is confined to the layer of fluid immediately adjacent to the solid wall. So this layer is called the boundary layer. And outside the boundary layer, potential flow survives, right? So I think I'll speak about that just briefly, and then we'll pick it up tomorrow. Yeah, I think we should. Okay, let me talk about it briefly. So what he's just saying is that if I have a pipe, oh no, there was a question. Let me address the question before I move to boundary layer flow. So the question was asking that thing, does the diameter of the pipe account for laminar or turbulence flow? Yes, it does. The diameter of the pipe would affect whether it's laminar or turbulent. So remember we spoke about that over here. Um, good. See here for small tubes, the flow is usually laminar. So we can have a very high velocity, but if the size of the tube is small enough, it wouldn't be turbulent, it will still be laminar. So that's the diameter of the pipe would affect whether it's going to be laminar or turbulent flow. Now, what Pranzo was saying was that if we have fluids that are moving at low velocity, so they are moving very slowly, right? Or they have high viscosity, so they are very thick. And the effect of the solid boundary on the flow is confined to a layer of fluid immediately adjacent to the solid wall. So it's similar to what we spoke about yesterday. As the fluid flows, remember we said that the fluid just above the solid surface is going to be stationary, right? What he's saying is that the um, the effect of the solid boundary on the flow is confined to just what is above the solid wall. So if we are using his parameters, and we are just saying that when the fluid is flowing just above the solid wall, the fluid molecules there are not going to move, right? And if we had a case where the viscosity was very low and the velocity was very fast, then even the fluid at the solid wall will not be affected by the boundary layer, right? Or by the boundary. So that layer is what we call the boundary layer. And outside the boundary layer, we can have ideal flow or potential flow. So outside the boundary layer, just above this point here, where our boundary is, right? The layer just above the boundary. So that's the boundary. And yes, just above that, we can have ideal flow happening. So we can have flow in this region and flow in this region, where we can assume the viscosity is zero. So eddies will not be formed. Is that okay? And I think that boundary layer is a region near a solid where the fluid motion is affected by the solid boundary. So there's a point where the fluid motion is going to be affected by the solid boundary. But when the fluid flows over the surface, the elements in contact with the surface will be brought to rest. So we spoke about that. When the fluid is moving over the surface, the elements in contact with the surface, that's just the fluid and molecules just at the surface, right? Those ones are going to be brought to rest because they are adhered to the solid surface or they are stuck to the solid surface, right? And then the adjacent layers will be retarded by the viscous drag of the fluid. So once again, we spoke about it. So realize that the fluid molecules just above the solid surface are at rest, and they are going to slow down the molecules above them, which will also slow down the molecules above them, which will also slow down the molecules above them, right? So the velocity in the neighborhood of the surface will change with distance perpendicular to the flow. So that's where we had our velocity gradients coming in. So we actually spoke about this in yesterday's discussion. We used the same animation and we spoke about this particular thing in yesterday's discussion, right? But then the thing right now is the whole issue of the boundary layer and the boundary layer flow. Remember we said that when we have, let me start with this animation here. When we have our fluid moving, it's just above the surface of the fluid. We are taking it that the molecules there are not going to have any velocity, right? They're not going to have any velocity, right? One thing about the boundary layer flow is that as the molecules are slowing down the ones above them, it gets to a point where the ones above them also now seem to become stationary, right? So it gets to a point until the velocity of the fluid is high enough that it cannot be retarded for it to become stationary. So let's look at it from this perspective. Let's say you have a number of people who are, I want to give a very good example with this. Okay, let's say you have Okay, good. So let's say we are playing with a football or something, right? And then you kick the ball, it has a certain velocity. But then let's say you kick it over a very rough surface. You realize that as time goes on, the ball starts to slow down and then it stops eventually. You get it. So it's being retarded by something. And over here, we know that the thing that is going to cause something to be retarded is the layer just below it. So we can have a point where it retards enough for it to become stationary. But what I'm saying is that if I should kick the ball with enough force and make it have an enough velocity, right, it might continue to go for a very long time. So the boundary layer, sometimes the boundary layer is not going to be just limited to just the solid surface here. The boundary layer can go because it's the point where the fluid particles are assumed to not be moving, right? So at this point here, all the particles just at the surface are not moving. But then at a certain point here, just some amount of the particles are not moving, and then everything else is moving. So just up to a certain limit, right? So let's say this is an entire fluid. Sorry, let me try and draw it better. So let's say that this is the entire everything here, right? From here, everything below this red line is fluid, right? What we're trying to say is that when we started out, just at the surface, there's going to be no flow. So when we see the broken line, it means that we are going to assume that that is the boundary layer. So at that point, the flow there has been greatly retarded, right? Just at this surface here, we are assuming that there is no flow. When we move further down, there's a certain velocity here. So over here, there is flow because it is above the broken line. But then remember, the particles are going to be um, retarded or slowing down the ones above it, just like the ball we kicked that was being retarded by the ground. It's going to be retarded by the ones below it. Also, it gets to a point where it also becomes stationary, right? Then the fluid up here as well will be retarded. It will have its velocity. It will be retarded until it gets to this point where now it looks as though it is not going to flow. So if you look at it, everything below this line, at this point here, below the broken line, forms what we call the boundary layer. So we are assuming that under that part, the fluid is almost stationary or is quite stationary. Above it, it is not stationary. So we can have what we call our ideal flow happening there. Is that okay? Now, the reason we are saying hydrodynamic boundary is because we are considering it in terms of the flow of the particles, right? We can have a boundary layer that is with respect to heat. So maybe at the surface of the wall, the fluid will have the temperature of the wall. So if the wall is at maybe 50 degrees Celsius, the fluid just above the wall will have a temperature of 50 degrees Celsius. But we can have a thermal boundary layer also forming. So for the thermal boundary layer, as soon as we get to the broken line, we assume that the temperature becomes exactly the temperature of the wall. As maybe the fluid has its own temperature. But then there's a certain region in the fluid where its temperature is going to be exactly the temperature of the wall. So the boundary layer is just this layer that ensures that the fluid has the properties of the wall. If it is with respect to heat, then it's going to have the same temperature as the wall. If it is with respect to velocity and motion, that's going to give us a hydrodynamic boundary layer. But it has the velocity of the wall, which in this case is zero. So we're assuming that it's not going to move, right? So that's just an overview of the boundary layer stuff, right? So we'll recap this before we continue tomorrow, and then we'll take it from there and we'll continue. Okay, so that's it for today. And I'll send the attendance link right away. But in the meantime, if there are any questions, please feel free to ask. Are there any questions? So I'm getting the link for us for the attendance for today. Are there any questions? Okay, so if there are no questions, then we can end it for today then. So that's the attendance. Let's use the next 5 minutes. We can fill it and then we'll be done.